My name's Elvis Jenga Kimani. I'm a civil engineer in background, but I'm also a nuclear engineer. I have a master's from Korea International University, where I did my master's in nuclear engineering. Well, I work for an institution called NUPEA. NUPEA stands for Nuclear Power Energy Agency, which is part of the Ministry of Energy. And their mandate is actually to carry out the development of nuclear infrastructure within the country. The purpose of this is that we want to set up a nuclear power plant into the power grid that will be actually be able to provide a base load of electricity for our country. Well, as you can see in front of you, this is what we call a HPR 1000 nuclear power plant. This is a power plant that is developed by China. The first one went into the grid in China last year, towards the end of last year. It was supposed to come out to go earlier, like 2 years before, but it went up last year. So this is one of the models that we are considering as a country of the nuclear power plant. If you can be able to see here, this is what we call the nuclear islands. It's composed of the containment building. This is where all the fission reaction occurs. The containment building has what we call pressurizers, because we heat water to 200 degrees Celsius, and for us to attain 200 degrees Celsius of water and maintain water as water, we have to do it under pressure, 2 atmospheres. The same way we'd have 1 atmosphere for 100 degrees for water to evaporate. Therefore, after water runs through these red pipes, these yellow pipes, it runs into the reactor. This is a nuclear reactor. In the nuclear reactor, there is fission reaction. That is a chain reaction whereby energy is produced and heat is produced, a lot of heat is produced. From the nuclear reactor, the water is heated and goes through these pipes, the yellow pipes, as you can see. And you can see they go round and come out towards the steel turbine. The steel turbine is here. The turbine generator is here. So at the turbine generator, the hot water goes, there's a counterflow of hot water from the reactor and cold water from other pipes within the structure. So what happens is during the counterflow, there is a heating of water without without radiation reaching the other water, because these waters are in different pipes. So you heat one pipe, it hits the other pipe heats water. And then once you heat the other pipe, you form water, the water goes to the turbines. This is what is called a conventional island. At the turbines, the water is turned to steam. The steam is turned to turbines and creates electricity, just like it happens in any other power plants. So the only difference is in terms of use of radiation at this section to produce heat. So what would happen is that for nuclear power plants, what we are supposed to avoid basically is radioactivity. Radioactivity reaching the external or the environment, or protect the nuclear power plant from the environment and protect people from the nuclear power plant. So you have two facets of how to do it. And that is why this wall, if you look at this wall, it's about 1 meter thick. 1 meter thick of wall. Even a Boeing 767 would fall on it and would not compromise what is inside here. That is how it is designed, so that you can avoid radiation going out of the containment building. Whatever the case, we try to have, even in a form of accident, if there exist accidents. There are 2 or 3 accidents that have been recorded in history for nuclear power. That is Chernobyl, 3 Mile Island, and let's work with those 2, and Fukushima Daiichi. So what happens is that if radiation is able to leave this part, then now we consider ourselves in an accident situation. And we have to find every other possible way to avoid radioactivity reaching the environment. Many people talk about how we take care of nuclear waste. As you can see from this side, there is something we call a spent fuel pool. This is what we call a spent fuel pool. Once you have used the nuclear fuel inside the nuclear reactor, they are pulled using this crane and they are driven underwater. See, this is a water pool, yeah? They're pulled from this crane, driven underwater to the spent water pool. In the spent water pool, this structure is designed in such a way that you can be able to handle fuel for 100 years. That is nuclear fuel. You understand radioactivity is a problem, so you have to be able to take care of that radioactivity within the nuclear power plants for a period of about 40 to 100 years. So normally for getting rid of waste, it is something that is not considered in the station of a nuclear power plant, normally by many countries. It's considered maybe in the 40th year going forward, simply because it's a process that within the power plant they have a mechanism of dealing with radiation. And I think that gives you a nutshell of this. You can see some of these things. This is core damage frequency. Core damage frequency is what's the probability of the core here being damaged by radioactivity. And if you look at the values, they are very low, 10 to the power 7, 10 to the power 5, 10 to the power 5, meaning that we normally say that it's easier to die from other things than a nuclear power plant. For example, an accident, the probability of you dying from an accident is 0.01. The probability of you dying from a nuclear power plant release is 0.0001%. So it is safe as a power plant. It is very safe in comparison even to air travel. And then if you look at large radioactive release, this is the release of radiation. You also have safe shutdown earthquake. This is dependent on seismicity. A nuclear power plant is normally affected by seismicity. If you remember the Fukushima issue, seismicity was able to affect. So for a value of 0.3 G, that's a good value, meaning that once an earthquake happens, the nuclear power plant can be able to withstand such a grand acceleration. And then in terms of design lifetime, the 60 years. Normally, in previous models, Generation 2 models were designed for 40 years, but these Generation 3 models have been designed for 60 years, 40 years with a 20-year potential of actually continuing to use the mechanism. Such a power plant would have about 1,000 megawatts equivalent of energy. That is half our grid in Kenya, just from one nuclear power plant.